In this video, I'm going to give some information about exponential growth and decay, and in particular the concepts of doubling time and half-life. So to begin, since I'm making this video in the middle of the COVID-19 epidemic, I thought I would give some information that's actually relevant to the current situation. One of these uh, one of these statistics that you'll sometimes hear is the doubling time for the number of cases. Early on in the pandemic, there were reports that the doubling time was every 4 days. And in some cases, it was even faster than that, every, say, 2.5 days. Well, what does it mean to have a doubling time of every 4 days? Well, it means that the number of cases is growing such that from any given day, if you wait 4 days, the number of cases doubles. So to give you some intuition numerically, suppose that we let t be time in days and we'll let q be the number of cases. And let's just suppose that we start out with, say, 1,000 cases. Well, after 4 days, that's doubled to 2,000 cases. After 4 more days, it's doubled to 4,000 cases. After 4 more days, it's doubled to 8,000 cases. So just to make sure it's clear what's happening, I'm adding 4 to the number of days that has passed in each line of the table, but the number of cases doubles. So this is very different from linear growth, where you would just add some fixed number of cases corresponding to the elapsed time. For doubling process, you multiply by 2 for each period of the doubling time. Now, at first, maybe this doesn't look so bad, right? I mean, we start out with 1,000 cases, and a couple of weeks later, we've only got 8,000 cases. But here's what happens if you keep going. After day 16, you have 16,000 cases. After day 20, you have 32,000 cases. And it just keeps going. By the time you've hit a month, so this is a month and a bit, after 32 days, we're at 256,000 cases. And by the time we get to day 40, we've hit 1 million cases. Technically 1,024,000. But just to give you that intuition, that's 1 million cases. This is a rough sketch of what growth like that looks like. So down here I have time in days, and I've been calling that t, and we'll let q be the number of cases. And you can see that in 40 days, we've gone from 1,000 cases to start with to over 1 million cases. This is what's so scary about an epidemic. It starts out and it doesn't seem to be all that bad, but then once it gets going, things get bad very, very quickly. For comparison, I looked up a statistic that said that the number of hospital beds in the entire United States is about 900,000. If you keep going with this, an epidemic that's growing such that it doubles every 4 days, by the time you get about 2 months into it, you've got hundreds of millions of people sick at the same time, and that's more than enough to completely overwhelm the entire hospital system. This is why we're doing all of this social distancing. It's to cut down the doubling time. Now, let me show you some graphs. This is data collected by the New York Times. What you are seeing here is, again, a time axis. Let me get to this here. You see here. All right, yep. So you see there's a time axis down here. And up here is one of these logarithmic scales for the number of cases. So just to make sure it's clear, well, that's not a good thing. I don't know where the graph starts. So each vertical step like that is an increase of a factor of 1,000. So you can see right there it says 1K, there it says 10K, there it says 100K. So each one of those steps is a factor of 1,000. That way you can see things more clearly. Over here to the left, you can see a line. This is, let me do this again. This line you can see cases double every 2 days. And at the beginning of the epidemic, New York City was seeing cases doubling faster than every 2 days. But now that social distancing has been in place, you can see the curve is starting to level off. And if I go back here and tap on it, it tells me the total case count is doubling every 12 days. So that means that the spread of the disease has slowed considerably. And that's what we have to have. We have to slow down the spread of the disease as much as possible to keep the hospital system from getting overwhelmed by these small but significant number of cases that develop into pneumonia and other complications. Now, to show you why that vertical scale is the way that it is, I'm going to first go over, let me cut this and paste it up here somewhere out of the way. And now I'm going to draw a different set of axes. Let me do these in blue. And this time I'm going to use that same technique on the vertical axis. This is a logarithmic scale. And here's what I'll do. I'll put in 1,000 cases here, and you can see that's 4 dots up. And I'm going to go up by a factor of 1,000. And it's not obvious where to put this, but that's about where 500 goes, and this is about where 500,000 goes. And now I can draw the same sort of thing. That's an 8. 28, 32, 36, 40. So on day 4, let's see, how many do we have on day 4? Oh, only 2,000. So that's not too bad. When did we get to... Oh, wait, we started at 1,000. My mistake. So we need to start at about 2,000, so right about there. We can skip a little bit better here. On day 36, we get to a little bit more than 500,000, and then on day 40, we get to a little over 1 million. So what you can see here, and my picture is a little bit crude, but what you can see here is that roughly when you use this kind of logarithmic scale, where each vertical step is a factor of so much instead of an added so much, exponential growth kind of straightens out, and the slope gives you some idea of the doubling time. So again here, going from 1,000 cases over here at time 0 up to just over 1 million cases, it takes 40 days to go up by that factor of 1,000. The doubling time is about 2 days. Okay, so it's the same data, it's just with a different scale on the vertical axis. Okay, so the moral of this is that doubling processes get big in a hurry, and that if you use a logarithmic scale, you can see a straight line instead of this abrupt curve that captures the same points. I'm not going to ask you in this class to draw graphs with a logarithmic scale, but since they've been in the news lately, I wanted to show you one again. Now, what exactly is the mathematical theory supporting something like this? Let me switch over to the slideshow. Here's the mathematical tool that we can use to understand this. So first, again, in contrast with a linear function, which has a slope, it has a slope-intercept form, y equals mx plus b. It has a point-slope form, y minus y1 equals m times x minus x1. The slope can be computed from any 2 points as rise over run, so y2 minus y1 over x2 minus x1. The new mathematical tool that we can use is exponential growth, which we set up like this. I'm going to let t be the independent variable instead of x. I'll let q be the amount of stuff that's growing exponentially. Depending on the context, that might be a population, it might be the value of something. Investments can sometimes grow exponentially. There's also something called a growth rate constant, which I'm going to call k. This is analogous to the slope m of a linear function. And there's also an initial quantity q sub 0 that's analogous to the b in y equals mx plus b. So here you see a graph of an exponential growth function. I've picked out 2 points, a t1 q1 and a t2 q2. And then here's the vertical intercept at time 0 and q equals q0. So here's the formula. Q equals q sub 0 times e to the kt. And this is for a growth rate, so I want the k to be greater than 0. Now, the growth rate constant you can actually compute from 2 points. I'll say in a minute where this formula comes from, but this is analogous to the formula for getting the slope of a line from 2 points. It's just that we have to do some additional calculations. Also, if you want to express the quantity q in terms of some point other than time 0 and the quantity at time 0, there is a way to do that using this point rate form that is analogous to the point slope form. Okay. So let me write this down. A general exponential function, q equals q sub 0 e to the kt. And I'm going to give a quick derivation of where that equation for k comes from. Okay, so here we go. We'll pick 2 points. So that's t1 comma q1 and t2 comma q2. Both of those points satisfy this function definition. So this is q is an independent variable, sorry, q is a dependent variable that depends on the independent variable t according to that equation. So I can plug both of those points into this equation for q as a function of t and get a more specific equation for just this point. So here we go. I get q2 is q0 e to the k t2, and I get q1 equals q0 e to the k t1. And I'm going to label these equations 1 and 2. Then for equation 3, I'm simply going to divide 1 by 2. If I have 2 equations, I can do left of the first divided by left of the second equals right side of the first divided by the right side of the second, like that. At this point, we can cancel the q sub 0. And that leaves us with the ratio q sub 2 over q1 equals e to the k t2 over e to the k t1. Now I'm going to use a property of exponents to simplify the right-hand side. Remember that if you have division, a base to a power, divided by same base to another power, you can simplify that to what? Base a to the m minus n. So I'm going to do that here using e as the base a, and then here's m k t2, and here's n k t1. Now I'm going to factor here because you can see that there's a k in both clusters of factors. So q2 over q1 equals e to the k times t2 minus t1. My goal here is to get a formula for k. At this point on the right, I have an exponential operation. So to get rid of that, I'm going to apply ln to both sides, which yields this equation, ln of q2 over q1 equals, and I think just for right now, I'll write it again like this. So ln of the whole left equals ln of the whole right. And the point of doing that is that ln of e to stuff simplifies to just the stuff, because the natural logarithm and the natural exponential function are inverses. Leaving q2 over q1 like that, I now have k times t2 minus t1 on the right. And now, to isolate the k, I just have to divide by t2 minus t1. So once I've done that, and I'll move the k to the other side, this gives me the formula that I was using, or that I showed on the slideshow a moment ago. So in other words, it is possible to calculate k from 2 points on the graph of q. Just like it's possible to calculate a slope of a linear function from 2 points on the graph of the linear function. So first, let me explain something about doubling. The doubling time is how long it takes for the quantity q to double from any reference value. And what this means is that you pick any starting time, you wait for the doubling time t sub d to elapse, and over that time the quantity will have doubled from whatever it was here. And you can use the formula that I just wrote down to get this formula relating k and the doubling time. So let me show you how to do that. It's relatively easy. So suppose you know the doubling time t sub d. Okay, so you pick a T1, and then you let that doubling time elapse to get to T2. So whatever Q1 is here, it will have doubled by the time you get to this point. So we're now going to say that T2 is T1 plus the doubling time, and Q2 is twice Q1. When you now fill in, I'm going to use this formula relating k to the 2 points on the exponential curve. We'll get ln of 2q1 divided by q1. So there I've replaced q2 with twice q1. And then underneath, well, if T2 is T1 plus TD, then if I subtract T1 from both sides, that would give me that T2 minus T1 is equal to TD. So I'll put that down here. And by the way, this is an equal sign. Now you simply cross out that factor, and you're left with k equals ln of 2 divided by the doubling time. So this equation says that every exponential curve has a doubling time that is related by this equation to its growth rate constant. You can also multiply by TD to get TD times K equals ln of 2, and then divide by K to get TD equals ln of 2 divided by K. So there's an equation there that tells you if you know the doubling time, here's how you calculate the rate constant. And this says if you know the rate constant, here's how to calculate the doubling time. And again, every exponential growth curve has a characteristic doubling time that you can calculate from its growth rate constant. Okay. Now, I've talked about the current COVID-19 epidemic. Not that long ago, there was an outbreak of the Ebola river virus. I collected some data from that and did some statistics. And you can see here that the purple curve is an exponential curve that approximately goes through the data that I have. And this was the result. And what you can see is that the rate constant K is 0.0221095. If you use this formula, ln of 2 divided by K, and you use this number for K, you'll get a doubling time of 31 days. So the Ebola virus, despite being much nastier than COVID-19, was not as big of a problem because its doubling time was so much slower. It's taking a month to double. The reason for that is that the Ebola virus is transmitted by fluid contact. Very often it was, say, blood to blood or blood to saliva from people handling corpses or from people handling a bleeding patient. But as long as you wear enough protective clothing, you can avoid direct fluid contact and prevent a lot of the transmission of the Ebola virus. Respiratory viruses are much harder to avoid. They just float around in the air. They tend to accumulate on surfaces that people touch. And so the COVID-19 virus has spread much faster, and its doubling time has turned out to be between 2 and 4 days when left unchecked. So there you go. One thing I should point out is that if you look at this curve, the curve matches the data very well up until about here. And now you can see that the curve is sort of undershooting and the data is sort of above it and looks like maybe about to turn down. That's because the epidemic grew very rapidly for a short time, but then people started to get it under control. Quarantine measures kicked in, and we were seeing many fewer cases per day, and so it was no longer growing exponentially at the same rate. That is also what we're seeing in this data from the New York Times, which is showing that initially cases in New York City were doubling every 2 days, which is even faster than the example calculations that I did earlier. But thanks to social distancing, as of the time that I'm recording this, the doubling rate has slowed. It's now doubling every 12 days. So it's no longer possible to model the COVID-19 outbreak in New York City by a simple exponential growth function as it was for the first, say, 2 weeks. And that's because we've put in social distancing measures and changed the dynamics of the disease. Okay, so that's exponential growth and doubling time. You can also talk about exponential decay. Exponential decay happens to substances where you have many different particles of that substance, and at any given instant, one of them has a certain probability of breaking down. It's commonly talked about in science classes when you study radioactive materials. Uranium, for example, will just spontaneously break apart and turn into a different element. And this, because of some mathematics that you can do, the result of this is an exponential decay process. Now, the usual convention for an exponential decay process is to use essentially the same equation as for exponential growth and have a positive decay rate constant, but you put the decay rate constant here with a minus sign. Effectively, this reverses the time axis so that exponential decay is what happens to exponential growth if you just flip it across the vertical axis. That's time reversal. And just like exponential decay or exponential growth, the things grow very quickly. In exponential decay, the first few steps of decay are huge, and then after a while, each individual, the amount of stuff has decayed down to the point that the absolute amount of stuff that decays from, say, one day to the next is not as much as it was to begin with. So that's, again, the difference between an exponential curve and a linear curve. The derivation for this equation for the decay rate constant is basically the same. You can also express Q in this point rate form. If you now consider, well, what must be the mirror image of doubling time? It must be some sort of cutting in half time, and that's something called the half-life. So the half-life, which I've denoted T sub h, is how long it takes for the quantity Q to decay to half of any reference value. And again, there's a relationship between the rate constant K and the half-life. And I won't go through it, but you plug in that Q2 is half of Q1 after a doubling time has elapsed, and you do the same kind of calculation that I did before, and interestingly enough, you end up with exactly the same formula. Part of why it's the same formula instead of, say, the same formula with a minus sign somewhere is that we stick the minus sign in right here. So these decay rate constants are positive. Just to give you some idea of the scale of these constants, for uranium, the half-life is on the order of 4 billion years, whereas for carbon-14, which is a radioactive form of carbon, it's just a few thousand years. Other kinds of radioactive isotopes have half-lives of just a few minutes or a few seconds, and they're used, for example, in medical imaging because you give a small dose to a person, and basically by the time they've left the hospital, most of it has decayed away. It's also possible to see ordinary chemicals break down according to exponential decay. So, for example, when you ingest medication, the active ingredient usually has a half-life of some kind because between your blood chemistry and other forces in your body, the medication does its work and individual molecules are destroyed over time. So there you go. That's doubling time and half-life and general exponential functions.